It's a pleasure to be with you. The title of this session is Immune Responses to Vaccines: Basic Concepts. There are no disclosures for this presentation. Objectives include review major concepts of innate and adaptive immunity, review vaccine-relevant concepts of placental immune transport, discuss the major attributes of innate and adaptive immunity, review the basic interactions of innate and adaptive immunity in response to antigen challenge, review the process of hematopoiesis and lymphopoiesis, discuss the importance of T and B cell memory, discuss conjugate and adjuvant vaccines, discuss the concept of immune tolerance, review the meningococcal B problem and how it was resolved, and discuss common assays used to measure immune responses to vaccines. Let's start by defining antigen, since that term will be used throughout this session. An antigen is any substance that causes the immune system to produce antibodies against it. An antigen may be a substance from the environment, such as chemicals, bacteria, viruses, pollen, etc. An antigen may also come from inside the body, like from cancer cells or self-antigens associated with autoimmune diseases. Antigens of bacteria or viruses are the immunologic targets for vaccines. A specific bacteria or virus may have myriad antigens. Some of these antigens are good targets for vaccines, like surface antigens, and others, like those internal to organisms, are generally not the most effective targets. Finding an appropriate antigen target is key to developing effective vaccines. The goal of vaccines or other immunotherapeutics is to develop or provide artificial immunity to prevent complications and death from pathogens. Immunity can be divided into two major categories: innate and adaptive. Innate immunity is a person's natural immunity built in from birth. Adaptive immunity is acquired immunity and can be subdivided into natural and artificial. Adaptive natural and artificial immunity can be passive or active. Examples of adaptive natural passive immunity would be the transfer of immunity from mother to baby during pregnancy, like the transfer of influenza and pertussis antibody that provides significant protection for the baby while he or she builds their immunity to these diseases through the immunization process. Let's briefly discuss placental transport of immunoglobulins or IgG antibodies, which are of major interest in maternal-fetal immune interactions and informs maternal immunization strategies. 60 to 70% of immunoglobulin G in the bloodstream is IgG1, followed by 20 to 30% IgG2, 5 to 8% IgG3, and 1 to 3% IgG4. The amount of the different IgG subclasses present in the bloodstream varies with age. IgG1 and IgG3 reach normal adult levels by 5 to 7 years of age. IgG2 and IgG4 levels rise more slowly, reaching adult levels at about 10 years of age. In young children, the ability to make IgG2 antibodies to the polysaccharide coatings of bacteria develops more slowly than the ability to make antibodies to proteins. Not all IgGs are equally transported by the placenta from mother to the fetus. IgG1 and IgG3 are transported much better than IgG2 and IgG4. IgG1 and IgG3 are stimulated by various non-polysaccharide antigens, including various proteins used in conjugated vaccines. This was shown when comparing immune responses to pneumococcal polysaccharide vaccine versus the pneumococcal protein conjugate vaccine, showing increased IgG1 in the conjugate vaccine group. IgG2 production is stimulated by polysaccharide vaccines. Therefore, the non-polysaccharide vaccines, including conjugate vaccines, will have greater transfer of protection for the baby than the straight polysaccharide vaccines. Placental transport via receptor mediation starts at 17 weeks gestation. By 33 weeks, maternal and fetal levels of antibody are equivalent, representing passive transfer. By 40 weeks gestation, active transfer of antibody kicks in, resulting in fetal antibody levels higher than those in the mother. Various conditions inhibit placental transfer, like HIV and malaria infections, also including other etiologies causing chorioamnionitis. This slide is adapted from a New England Journal of Medicine article in 2001. As mentioned previously, when a mother has IgG1 and IgG3 antibodies in her serum, placental transport starts at 17 weeks gestation and progressively increases, with maternal levels equaling fetal levels at 33 weeks, passive transport. By 40 weeks, fetal levels are greater than maternal levels, active transport. That IgG1 and IgG3 maternal antibody transferred to the baby provides significant protection against organisms for which the mother has immunity and lasts well into the first year of life, while awaiting the building of the infant's own immunity in response to their primary vaccination series, the protection triangle. Without that transferred immunity, that same triangle becomes a vulnerability triangle. This underlines the importance of vaccinating the mother to protect the infant. This slide lists important questions to consider related to maternal immunization strategies. Safety of mother and infant, immunogenicity of the vaccine in the mother, placental transfer. What type of immunity does the vaccine stimulate in the mother, and how effectively is this immunity transported to the baby? Polysaccharide-only vaccines primarily stimulate IgG2 that isn't transported as well across the placenta, where non-polysaccharide vaccines, including those with protein conjugates, stimulate IgG1 and IgG3 that are transported more effectively, resulting in a better triangle of protection. Timing is also important and depends on the target. For influenza, protection of the mother is primary, resulting in recommendations to immunize as early in pregnancy as possible. For pertussis, the prime target is to protect the baby more than the mother. Therefore, the preferred time to immunize is 27 to 36 weeks gestation, a peak time for maximal antibody placental transfer. Examples of adaptive natural active immunity would be the immunity acquired after an infection with viruses like measles, rubella, and hepatitis A. Examples of adaptive artificial passive immunity would be the use of IgG antibody from convalescent plasma given to susceptible individuals who are exposed and at risk of infection with organisms like measles, rabies, and hepatitis B. The plasma from convalescent individuals as a source of neutralizing antibodies for use in passive immunotherapy has been used for the treatment or prevention of many viral infections, including measles, Ebola, Junin virus, cytomegalovirus, CMV, respiratory syncytial virus, RSV, smallpox, hepatitis A and B, and rabies. Examples of adaptive artificial active immunity would be immunizations. The CDC demonstrated that the lifespan of Americans increased by approximately 30 years from 1900 to 1999. 25 of those years were due to public health interventions. 5 years could be attributed to healthcare advances, including medications like antibiotics, surgical technology, or life support. The 10 health achievements that significantly impacted lifespan in the 20th century included immunizations or vaccinations, motor vehicle safety, safer workplaces, control of infectious diseases, including water protection, sanitation, etc., declines in cardiovascular heart disease and stroke deaths, safer and healthier foods, healthier mothers and babies, family planning, fluoridation of water, and recognizing tobacco as a health hazard. Of this list, immunizations are considered the most effective public health tool in history. Let's discuss innate and adaptive immunity interactions in response to antigens, including those associated with immunizations. As mentioned previously, innate immunity is a person's natural immunity built in from birth. Innate immunity is not specific and therefore doesn't focus on a particular organism like pneumococcus or influenza, but it does recognize organisms invading the body and responds to that invasion. Innate immunity has no immune memory, therefore is not enhanced by future exposures to the same organism. Examples of innate immunity include the activities of several cells, including neutrophils, monocytes, natural killer cells, and dendritic cells in response to offending antigens. Dendritic cells are abundant at body surfaces and within tissues where they sense and sample the environment for self and non-self antigens. Innate immunity is not very effective in and of itself without adaptive immunity. Having said that, innate immunity functions are essential for optimal adaptive immune responses. Adaptive immunity is acquired or learned by experience with a specific pathogen like influenza, pertussis, measles, COVID-19, etc. Adaptive immunity is enhanced by subsequent exposures and results in immune memory. Adaptive immunity has cellular and humoral or antibody components. Adaptive immunity effects are significantly reduced in the absence of innate immunity. This diagram outlines a few basic interactions of innate and adaptive immunity in response to antigens. Innate immunity is not dependent upon prior antigen exposure and does not result in immunologic memory. Adaptive immunity develops memory through memory B and T cells. The immune response often is initiated in areas of inflammation. Inflammation commonly occurs where vaccines are injected. That inflammation is generally mild but can result in soreness and redness about the injection site and indicates the body's immune reaction to foreign material. Inflammation is initially caused by the innate immune system. Inflammation is part of a complex biological response to injury caused by the invasion of pathogens, damaged cells, or irritants. This local injury results in an innate immune response where cells are mobilized to the site of injury, including polymorphonuclear leukocytes, PMNs, dendritic cells, macrophages, monocytes, etc. This initial inflammatory response to an injury or invasion of a pathogen stimulates additional innate and adaptive immune responses. The innate and adaptive immune systems coordinate to respond to the foreign pathogen or antigen. Innate immunity is composed of three basic components. 1. Anatomic barriers. 2. Cells, and 3. Soluble proteins. Innate immune cells include granulocytes, basophils, eosinophils, neutrophils, mast cells, natural killer cells, dendritic cells, gamma delta T cells, natural killer T cells, and macrophages. Innate soluble proteins consist of cytokines and the complement system. As previously mentioned, innate immunity activities are essential for optimal adaptive immune responses. Following antigen exposure, both the adaptive and innate immune systems can be activated. Virus-containing cells and tumor cells can directly activate natural killer cells of innate immunity. Natural killer cells, NK cells, are a subset of large granular cytotoxic non-B non-T peripheral blood lymphocytes that appear to play a crucial role in the human innate immune response. The role of NK cells is analogous to that of cytotoxic T cells in the adaptive immune response. NK cells provide rapid responses to virus-infected cells, acting at around 3 days after infection. They also respond to tumor cells. Typically, NK cells detect non-self major histocompatibility complexes, MHCs, presented on infected cell surfaces. These non-self MHCs trigger a cytokine release, causing the death of infected cells by lysis or apoptosis. Apoptosis is a form of programmed cell death that occurs in multicellular organisms and is associated with cell shrinkage, nuclear fragmentation, chromatin condensation, chromosomal DNA fragmentation, and global mRNA decay. The average adult human loses between 50 to 70 billion cells each day due to apoptosis. Let's briefly discuss major histocompatibility glycoprotein complexes, MHC1 and 2. MHC1 glycoproteins are present on almost all nucleated cells and are unique for individuals. In other words, MHC1 glycoproteins identify cells that belong to an individual, identifying self from foreign cells. MHC2 glycoproteins are only present on specialized antigen-presenting cells, APCs, including macrophages and dendritic cells of the innate immune system and B cells of the adaptive immune system. NK cells are unique, however, as they have the ability to recognize and kill stress cells in the absence of antibodies and non-self major histocompatibility complexes, MHC1s, allowing for a much faster immune reaction. This is especially important since harmful cells that are missing those non-self MHC1 markers cannot be detected and destroyed by other immune cells, such as cytotoxic T cells. Offending antigens are also presented to the adaptive immune system by antigen-presenting cells, APCs. Antigen-presenting cells include adaptive system B cells, both naive and memory, and innate system macrophages and dendritic cells. APCs present antigens to CD4 T helper cells that stimulate B cell formation of plasma cells and produce antibodies. Those antibodies attached to antigens initiate a complement cascade of the innate immune system. The complement system, when activated by an antigen-antibody complex, enhances the ability of antibodies and phagocytic cells to clear microbes and damaged cells, promote inflammation, and attack a pathogen's cell membrane. APC-presented antigens also result in other adaptive T cell functions, resulting in CD8 cytotoxic T cells and CD4 T helper cells through clonal expansion and differentiation. Adaptive processes also stimulate gamma delta and natural killer T cells that are part of the nonspecific innate immune system. Natural killer T cells provide cell-mediated cytotoxicity against pathogen-infected cells. Gamma delta T cells release cytokines. Cytokines include interferon, interleukin, and growth factors, which are secreted by effector cells that impact the activities of adaptive and innate immune processes, like inducing cytotoxicity, regulating cellular immune responses, and stimulating mucosal immunity, etc. This diagram demonstrates the organs of the immune system in humans, including the tonsils and adenoids, lymph nodes and lymphatic vessels, the thymus that provides various T cells, the spleen, Peyer's patches, the appendix, and the bone marrow where stem cells develop into various immune cells of the adaptive and innate immune system. Lymphocytes are a major component of the adaptive immune response, so let's discuss lymphocytes for a few minutes. A lymphocyte is a type of white blood cell. Lymphocytes include natural killer cells, which function in cell-mediated cytotoxic innate immunity, T cells for cell-mediated cytotoxic adaptive immunity, and B cells for humoral antibody-driven adaptive immunity. They are the main type of cell found in the lymph system, which prompted the name lymphocyte. Lymphocytes make up between 18% and 42% of circulating leukocytes, or white cells, in the body. Let's discuss the body's process of creating lymphocytes using this simplified diagram. Stem cells differentiate into several kinds of blood cells within the bone marrow by a process called hematopoiesis, including development of common lymphoid progenitor CLP cells. All lymphocytes originate from these common lymphoid progenitor cells by a process called lymphopoiesis. These common lymphoid progenitor cells eventually differentiate via the process of lymphopoiesis into various lymphocyte types, including T cells that provide cell-mediated cytotoxic adaptive immunity, B cells for humoral antibody-driven adaptive immunity, and natural killer cells which function in cell-mediated cytotoxic innate immunity. Immature T cells migrate from the bone marrow to the thymus, where they are called thymocytes. These thymocytes mature in the thymus to T helper cells, CD4 cells, and cytotoxic T lymphocytes, CD8 cells. Following maturation, the T lymphocytes, CD4 and CD8 lymphocytes, enter the circulation and peripheral lymphoid organs, including the spleen and lymph nodes, where they survey the body for invading pathogens and/or tumor cells. Immature B cells migrate from the bone marrow to lymphoid tissue and differentiate into plasma cells that produce antibodies and B memory cells. This maturation and differentiation of B cells occurs within germinal centers, GC, or sites within lymphoid tissues, the lymph nodes, and the spleen. The lymphocytes involved in adaptive immunity, the B and T cells, further differentiate after exposure to a pathogen or antigen by forming specific effector and memory lymphocytes. Effector lymphocytes function to eliminate the pathogen, either by releasing antibodies from B cells, cytotoxic granules from cytotoxic T cells, or by signaling other cells of the immune system via helper T cells. Memory T cells remain in the peripheral tissues and circulation for an extended time, ready to respond to the same antigen upon future exposure. It takes about 20 days for the formation of adequate memory B and T cells during the adaptive immune process. Memory B cells arise from T cell dependent reactions within germinal centers of peripheral lymphoid tissues. Memory B cells and memory T cells are critical for enhanced immune responses when re-exposed to an antigen. Memory B cells do not secrete antibody. Following a second challenge with an antigen, memory B cells present antigens to memory T cells. B lymphocytes are one of the three major antigen-presenting cells, APCs, along with macrophages and dendritic cells. Antigen-presenting cells have major histocompatibility complex II, MCH2, and B7 receptors, key for stimulating T helper cells. These T helper cells, CD4 cells, cause plasma cell formation from B cells and possibly stimulate the formation of other secondary germinal centers, GC. This memory B cell and memory T cell process allows for a rapid, coordinated response to re-challenge from a pathogen that occurs much more quickly than a primary response from naive B and T cells. Memory B and T cells may remain viable for years. This memory response process is critical in providing disease protection via immunizations. Let's now discuss conjugate and adjuvant vaccines. Conjugate vaccines generally target the adaptive immune system, and adjuvant vaccines generally target the innate immune system, though there is significant interaction of these systems in response to these vaccines. Vaccines evoke a primary immune response to an antigen, and the immune system reacts by producing T cells and antibodies. The B and T cells develop a memory for that antigen so that if the body encounters it later, specific antibodies can be quickly produced to bind to the antigen, initiating secondary innate and adaptive immune responses. For bacteria with a polysaccharide coating without a conjugate, the immune response stimulates B cells directly, independent of T cell stimulation, resulting in a minimal antibody response. By conjugating the polysaccharide to a protein carrier, a conjugate, a helper T cell response can be induced. Common proteins used for conjugation include diphtheria toxoid and tetanus toxoid. Normally, polysaccharides by themselves are not recognized by the major histocompatibility complex II, MCH2 receptors of antigen-presenting cells, APCs, because the MHC2 receptor can only bind peptides. Peptides are protein-containing compounds consisting of two or more amino acids. A conjugate vaccine links a carrier peptide to the polysaccharide target antigen, which enables binding to the MHC2 receptors of an antigen-presenting cell, APC. The APC can then present the bound antigen, the polysaccharide linked to the conjugate, to helper T cells, which stimulate B cells to produce large amounts of specific antibody against the antigen. Along with stimulating a more vigorous antibody response, conjugation also promotes a more rapid and long-lasting immunologic memory via both memory B and T cells. Memory B and T cells may remain viable for years. Children under 2 years of age don't respond well immunologically to polysaccharide antigens in bacterial pathogens or vaccines. Conjugation of a polysaccharide antigen to the conjugate protein increases the immune response of children under 2 years of age to vaccines. For example, there are 2 pneumococcal vaccines in the United States: pneumococcal polysaccharide vaccine, PPSV23, and pneumococcal conjugate vaccine, PCV13. The polysaccharide antigens in PPSV23 are T-cell independent, meaning that they directly stimulate B cells to produce antibody. T-cell dependence is necessary for the booster response. Therefore, PPSV23 revaccination does not result in a booster effect. PPSV23 does not develop significant antibody responses in children less than 2 years old. Conjugate vaccine responses are T-cell dependent, presenting antigens to T helper cells and B cells, enhancing antibody response. Conjugate vaccines like PCV13 stimulate the development of both T and B memory cells that result in a long-term booster effect with antigen rechallenge. PCV13 develops adequate antibody responses in children less than 2 years old. So who should get PPSV23? CDC recommends that 1 dose of PPSV23 should be given to all the following immunocompetent individuals: all adults 65 years or older, people 2 through 64 years old with certain medical conditions, including asthma, COPD, chronic heart disease excluding hypertension, diabetes, alcoholism, and chronic liver disease. Adults 19 through 64 years old who smoke cigarettes should also receive PPSV23. So who should get PCV13 vaccine? The CDC recommends PCV13 for all children younger than 2 years old, with catch-up dosing per the CDC schedule through 6 years old. People 2 years old or older with immunocompromising conditions, cerebrospinal fluid leaks, and cochlear implants. Immunocompromising conditions include chronic renal failure, nephrotic syndrome, immunodeficiency, iatrogenic immunosuppression, generalized malignancy, human immunodeficiency virus, Hodgkin's disease, leukemia, lymphoma, multiple myeloma, solid organ transplants, congenital or acquired asplenia, sickle cell disease, or other hemoglobinopathies. In addition, adults 65 years or older may discuss and decide with their clinician to receive PCV13 through a process called shared clinical decision-making. Examples of conjugate vaccines to enhance immune responses to bacterial polysaccharides include quadrivalent meningococcal vaccine, Haemophilus influenza type B vaccine, pneumococcal conjugate vaccine PCV13 that we just mentioned, and typhoid conjugate vaccine. Adjuvants act by initially enhancing innate immunity. Adjuvant benefits include a more rapid response to pathogens. This is particularly important when used in post-exposure prophylaxis. An example of this use of adjuvants would be the Pica adjuvanted rabies vaccine. Adjuvants help overcome immune senescence in the elderly. The Shingrix recombinant adjuvanted vaccine would be an example of this. There have been 2 varicella-zoster or shingles vaccines used in the United States. Zostavax is no longer available in the United States as of November 18, 2020. Zostavax was a live attenuated vaccine with 16 times the dose of virus versus the childhood vaccine called Varivax, also produced by Merck. Shingrix is a GlaxoSmithKline vaccine, non-live, subunit vaccine utilizing an adjuvant protein E located in the glycoprotein spike of the virus envelope. Shingrix requires 2 doses, separated by 8 weeks. This slide demonstrates the advantage of using an adjuvant to prevent shingles and a complication called post-herpetic neuralgia, PHN, or debilitating chronic pain post-shingles. Zostavac's effectiveness dropped dramatically from the 50-year-old to 80 and older age groups, 70% to 18%. Shingrix, the adjuvanted vaccine, demonstrated increased effectiveness in preventing zoster or shingles across the age ranges, 97% for the 50 to 59-year-old group and 91% in those 80 and older. Zostavax had a protective effect against PHN of about 66% versus 90% for Shingrix. This is an example of overcoming immune senescence in the elderly using an adjuvanted vaccine. Adjuvants save resources by decreasing the amount of antigen used for vaccines or therapeutics. Adjuvants have potential in the development of new vaccines for tuberculosis, influenza, HIV, malaria, HPV, etc., and the treatment of cancer. Adjuvants enhance response to vaccine antigens. A good example would once again be Shingrix, a recombinant adjuvanted varicella vaccine to prevent shingles and its complications. Adjuvants can also reduce the number of immunization doses required to reach a protective threshold. An example of this would be Heplisav-B, an adjuvanted hepatitis B vaccine that requires 2 doses versus 3 doses of other hepatitis B vaccines. This table lists common adjuvants used to stimulate innate immunity and vaccines that use those adjuvants. Aluminum is the most commonly used adjuvant in a variety of vaccines, including anthrax, DTaP, IPV, hepatitis A and B, Haemophilus influenza B, HPV, Japanese encephalitis, meningococcal B, pneumococcal, TD, and Tdap vaccines. Cervarix uses ASO4, a mixture of monophosphoryllipid A, MPL, and aluminum. Fluad, an influenza vaccine for those 65 years old and older, is adjuvanted with MF59, an emulsion of squalene oil and water. Shingrix, a varicella vaccine for individuals over 50 years old to prevent shingles, is adjuvanted with MPL and QS21, an extract from the Chilean soapbark tree combined in a liposomal formulation. Heplisav-B, a hepatitis B vaccine, is adjuvanted with cytosine phosphoguanine, CpG. How adjuvants impact vaccine response is not fully understood, but here are a few examples. Aluminum adjuvants can trigger the antigen-presenting cells, APCs, the innate immune system's dendritic cells, along with other immune cells to secrete cytokines, like interleukin-1 beta, that promotes adaptive immune antibody production. Monophosphoryllipid A, MPL adjuvants interact with toll receptor TLR4 that signals inflammatory cytokine production to activate the innate immune system. Immune tolerance prevents the immune response from destroying the host cells. The immune process identifies a foreign pathogen or antigen and results in proliferation of immune cells to destroy the foreign pathogen or eliminate the antigen. Antigens from the host cells are protected by two tolerance mechanisms, central and peripheral tolerance. Central tolerance results in deletion of activated cells by a process called apoptosis. As previously discussed, apoptosis is a form of programmed cell death. Peripheral tolerance is accomplished through two main processes: inactivation of cells, also called anergy, and suppression of cells mediated by regulatory T cells. A detailed discussion of immune tolerance is beyond the scope of this session. Let's consider the meningococcal B vaccine problem and how it was solved. Brain polysaccharide is very similar to meningococcal B polysaccharide. Therefore, antigen-producing cells, APCs, can't recognize meningococcal B polysaccharide as foreign. This problem was solved by identifying non-polysaccharide targets located on the outer membrane vesicle of the organism. There are currently two effective meningococcal B vaccines for individuals 10 to 25 years old in the United States: Trumenba and Bexsero. Trumenba is a Pfizer vaccine licensed in 2014. Trumenba targets a non-polysaccharide outer membrane vesicle OMV component, factor H binding protein, FHBP. Trumenba uses aluminum as an adjuvant. Bexsero is a GlaxoSmithKline vaccine licensed in 2015. Bexsero utilizes aluminum as an adjuvant and targets four outer membrane vesicle OMV components: NHBA, NADA, FHBP, and PORA. Both meningococcal B vaccines result in complement-mediated, antibody-dependent killing of the organism. Common assays used to measure immunity include antibody, serum bactericidal, and T cell assays. A detailed discussion of these assays is beyond the scope of this session. There are three categories of assays for measuring antibodies: immunogenicity, quality, and functionality. Immunogenicity assays determine if the antibody binds to the antigen. Quality assays determine the avidity, veracity, or tightness of antibody-antigen bonds. Functionality assays include opsonophagocytic and neutralization assays. Opsonophagocytic in vitro assays determine whether vaccine-induced antibodies result in complement deposition and subsequent opsonophagocytic killing of the target pathogen. Neutralization assays determine the titer of a patient's serum that neutralizes a pathogen, measured as the serum dilution that causes cell death in cell cultures infected with a target pathogen. So neutralization assays measure the protective level of antibodies generated by a vaccine. In the picture of a neutralization plate shown, cell death was noted at a titer or dilution of 1 to 16, and neutralization or protection was demonstrated at a titer of 1 to 8. Serum bactericidal assays are used to determine if a patient's serum antibodies will kill a targeted bacteria. Serum containing anti-capsule antibodies is mixed with rabbit complement and phagocytes and applied to a standard agar plate inoculated with a target bacteria. The plates are then incubated and observed for whether the mixture was bactericidal, killing the organism or not. T-cell assays, like antibody assays, look for immunogenicity, quality, and functionality. Immunogenicity may be determined by a gamma interferon assay, for example, ELISpot. The enzyme-linked immunosorbent spot assay, ELISpot, is a type of assay that focuses on quantitatively measuring cytokine secretion like gamma interferon. ELISpot is performed by first coating a plate with captured antibody, followed by adding immune T cells from a patient. Antigen is then added to the plate. The plate is then incubated. Cells are removed, and the released cytokine is measured by using a chromogen or a reagent that provides a color in a reaction with that cytokine. The quality of T cell immunity is often measured by flow cytometry or antigen sensitivity, or the amount of antigen needed to stimulate a T cell response. Functionality is determined by the ability of a patient's T cells to suppress or kill pathogen-infected cells. The quality of vaccine immune responses is dependent on the vaccine type. Toxoids and surface molecule vaccines result in a dominant antibody response with some T helper cell input. Attenuated bacteria and inactivated virus vaccines result in a significant antibody and T helper cell response. Attenuated virus vaccines result in significant antibody, T helper cell, and killer T cell responses. Attenuated virus vaccines are generally the most effective since they incorporate more components of immunity. Neutralizing antibodies are the primary correlate of the ability of vaccines to prevent infection. In summary, the goal of vaccines or other immunotherapeutics is to develop or provide artificial immunity to prevent complications and death from pathogens. Finding an appropriate antigen target is key to developing effective vaccines. Adaptive immunity effects are significantly reduced in the absence of innate immunity. Lymphocytes are a major component of the adaptive immune response. It takes about 20 days for the formation of adequate memory B and T cells during the adaptive immune process. Conjugates and adjuvants enhance vaccine efficacy. Immune tolerance prevents the immune response from destroying the host cells. Neutralizing antibodies are the primary correlate of the ability of vaccines to prevent infection.